So let's just do kind of a review. So at least the start of a review. I'll do all the structured review today, and then just open it up for basically extended office hours from here on out. Again, final exam. Since the final exam is going to emphasize the new stuff, so homeworks 8 through 10, right? Since it's going to emphasize that stuff with one of the long answer questions or equivalent being on that and then being featured more heavily in the multiple choice questions, I'm obviously going to focus my review starting on the new stuff, right? If I have time to talk about exam 1 through 2 stuff, I will, but you've got such a variety of materials at this point to look at. You've got the actual and practice midterms. You have not only the practice midterms I posted in your actual midterm, you have the other sections midterm too. I posted that, so you have an extra practice exam right away for both of the first 2 exams. So let me focus on homeworks numbers 8 through 10. No, why don't you find? Yeah, is that right? Yeah. Okay. But it is cumulative. So I'm not going to do anything magical or anything. I'm just going to kind of talk through the topics, remind you of the major gists in that stuff. So let me just have this stuff out so I can refresh my memory here. I seem to be missing a page. That's a bummer. Homework number 8, that was kind of like the beginning of light, so light basics. Homework 9 was all about mirrors and lenses. And homework 10 was basically your physical optics and your modern physics. Okay, so let's talk about light basics. For basics, you have light as a wave. It is a variation of the electric and magnetic field. Etc. Things you might want to know, that these are mutually perpendicular. E is perpendicular to B, is perpendicular to the V, the direction of motion. Of course, V equals F lambda. If you ever want to convert between speed, or know the relationship between speed, frequency, and wavelength, always have that handy. The speed of light, in a vacuum it's c, and then in any other material it slows down, and we use the index of refraction for that. We find that the wavelength also will compress. And the only thing that you can count on being the same when you go into a material is the frequency. So that's important to remember, is that the frequency you can always count on. So red light is red light is red light. It has a given frequency no matter what its wavelength might change to as you go to different materials. One of the things that we did right off the bat was talk about something called polarization, where the only thing we really cared about was in what plane is the electric field going to oscillate. We recognize that we don't really care about the electric field itself, we care about intensity, which is related to its square. And so we came up with something called the law of Malus, which told us what is the output intensity like relative to the input intensity. And there's a cosine squared function. And let me remind you what that is. That is when you have light that is already linearly polarized, it comes through this thing called a polarizer, which has a thing called the transmission axis. And when it comes in, what you want to do is you want to measure the angle between the incoming polarization and the transmission axis. Okay? So that is between the incoming polarization, remember it's incoming, and the transmission axis. So if you remember that, oftentimes you forget, sometimes students forget that what comes out is of course the only thing that managed to slip through, so what comes out is parallel to the transmission axis. And the reason why that's important is because if you're going to go through another polarizer, then you need to make sure that the light comes in a different orientation than it did through the first. Okay?
Question?
Yeah.
Just before we go too far ahead.
Mm-hmm.
The thing that your eye cares about when you see light is frequency, right?
Frequency and intensity, right? So frequency is the color and intensity is the brightness.
Okay.
Other things to remember is that for unpolarized light, I out is just I in over 2, okay? So the law of malice really just works with if your light is already linearly polarized, because then you can say it has a definite incoming, it definitely has an angle between the incoming polarization and the transmission axis. If it's unpolarized, just have it. And don't forget, of course, when it comes out, it's not unpolarized anymore. All light, when it emerges from a polarizer, will be parallel to the transmission axis. So that's polarization through this special thing called a polarizer. It's also possible to have polarization of light when it reflects. And so basically, if you have light bouncing off a surface, the polarization will be largely parallel to that surface. In our case, we mostly have surfaces that are flat, horizontal, and so mostly the light will be horizontally polarized. It won't be perfectly, but it'll be very largely horizontally polarized. So you send in all polarizations, when it reflects, it's highly polarized. For sunglasses, you're mostly looking at surfaces that are flat, maybe the road or the lake or something like that, and so inevitably you want your transmission axes on your sunglasses to be vertical. That means that it blocks out the most horizontally polarized light. And of course, don't forget, if all sunglasses are going to have vertical transmission axes, if you're going to have any kind of polarized light display, like a digital watch or something like that, you want that the light that comes off of that is vertical, because then they can get through your sunglasses instead of going black. Okay? So any kind of display that puts off polarized light, you want to make sure it gives off vertically polarized light if you possibly can. Okay, so that's polarization. And then after some of those just kind of basic topics, we moved almost exclusively into geometrical optics, where all of our light beams for a while were just rays. That would take you through the rest of that homework, and homework 8 and all of homework 9. So first things first, when light comes in, we of course always measure the angle that it makes to the normal. That's your incident. And in general, light will both reflect and refract. So generally speaking, you will get both beams. This is the reflected angle. This is the refracted angle. And the law of reflection is quite straightforward. Equal angles. I don't think we did really a whole lot with that, except as it was applied to mirrors. There's a little bit more to chew on with the refracted beam. We get the law of refraction, or Snell's law, which I believe you studied. I can't remember if you did the lab this semester. You kind of bent light through this like D-shaped thing.
Yeah.
Did that one? Okay. So there you should have definitely on lockdown the bending toward and away from the normal business. So remember, if you go into a bigger end, you bend toward the normal. And if you're in a bigger end going into a smaller end, you bend away from the normal. Like so. If you're bending away from the normal, oh, and I guess I should say, remember too that not only is it bending toward or away from the normal, but how much you bend is how different are the end values. So the larger end difference equals larger bending. So if you have a stark difference in end values, that's a big bend. If the end values are very close to each other, you'll get very little bending. And of course, in the limit that the end value doesn't change at all, you won't bend just because you feel like it. There's no bending anymore at all. I guess the other thing I should mention is remember that the bending only happens for angles above 0. Oh, not equals. There we go. So any light beam that comes in along the normal just goes straight through. The bending business only starts to happen if the incident angle is something. Okay. And then, as far as bending away from the normal, we have access to an extra phenomenon called TIR, total internal reflection. And the whole idea there is that you can bend so far away from the normal that you don't actually make it into the second material. So you can bend like this, and basically that angle is 90. So when the incident angle is the critical angle, then the transmitted angle goes to 90, which really means that it didn't actually enter that second material. So that fact allowed us to solve for an angle, the formula for the critical angle. Remember what's going on here. NT, that's the material that you're bouncing off of but unsuccessfully now refracted into. And N sub I is the material that you started in and stay in too, because you didn't actually make it out into NT. So that formula is of course available for you. You don't have to necessarily remember where it came from, but you do have to learn how to know how to use it, right? So things that you have to remember that go along with total internal reflection that aren't just the equation. First of all, you can only have it. So only have it if NT is less than N sub I. It only works if you're bending away from the normal, okay? And secondly, this is just where the party starts. So any incident angle that's bigger than the critical angle is also just fine. The critical angle is the minimum angle. It's the minimum bar you have to clear for this to start working, but then you'll get total internal reflection for any bigger angle than that too. So remember that the critical angle is just the minimum angle where the whole thing starts. So anything bigger than that is fine too. So if this is the critical angle, total internal reflection will be from here on forward. And I guess also as a reminder, if you have stark end value differences, the bending will be stark, and so it's easier to get this thing started. So you will find that if N sub I is larger compared to N sub T, which is usually air, okay? If N sub I is larger, then the critical angle will be smaller. This is not, total internal reflection is a lot easier to achieve. The minimum bar you have to clear to get it started is lower if you have a stark difference in end values to begin with. And I talked about the fact that diamond is particularly easy to make this happen because diamond has such a large end value compared to airs. So that's total internal reflection. And again, let me remind you that this beam essentially disappears. It would rather die than stay in the limbo between the two things. And at this point, we usually remember that we do have a reflected beam as well, where now 100% of the light will go there. So if in general, you always get both beams, in this case, it's all reflected. That's why it's called total reflection. And it's called total internal reflection because it's trapped inside the material and not able to escape to air. So that is the gist of that stuff. And then the final thing on that homework was dispersion. And that whole idea of that is that n, the index of refraction seen by a material, is somewhat wavelength dependent. So that means that if white light enters a material, all the colors will slow down, but not all in equal amounts. And if they don't slow down in equal amounts, they don't bend in equal amounts. And this is what allows us to separate colors out. If we're clever with how we do it through a prism, we can drive a progressive wedge and fan out the colors differently. Remember that the typical dispersion profile for many things like glass and water looks like this. So the n value decreases with wavelength. So if you put in Roy G. Biv here, again, remember that compared to the baseline of 1, so if you're talking about entering a material from a vacuum or air, violet is going to see a much starker end change, and so it's going to bend more so. So that's where the mnemonic comes from. Violet bends most violently. So remember that violet is going to bend more towards or away from the normal in any situation compared to red, has much weaker changes in comparison. So that takes care of homework 8. I'm going to do a brief synopsis of mirrors and lenses. Again, this is very, very workmanlike, so just kind of a lot of this stuff I didn't derive. I'll just kind of quickly summarize. So for mirrors and lenses, the object distance is always going to be positive for us. It can be negative, but that's beyond the scope of the course. Di is positive if it's at the same side as the outgoing light. It's tied to the outgoing light. We have that focal length is positive for a concave mirror and a converging lens. And F is always negative for a convex mirror and a diverging lens. And I guess let me remind you, the easier case is definitely the convex mirror and the diverging lens. Those always scatter light. So just as an example, if I have my diverging lens, I send in light like this, it scatters it. The image is always going to be back here somewhere. So the object is over here, the image is over here. This image distance is going to be negative because it's on the opposite side as the outgoing light. And we basically are always on the DI is negative, magnification is positive, we have a virtual image, and we have, what's the last one? Upright? Upright, yeah. So you're basically always variations of a theme there. The easiest way to kind of remember how everything moves is to just remember what it has to be at the beginning and what it has to be at the end. So when the object is really far away, image is always at the focus. That's the definition of the focus. So when the object is at infinity, the image is at the focus. And when the object, basically you stick it right on the glass or the lens, you have to wind up with plane mirror or pane of glass behavior. So what you have to have by then is that the object and image have merged. They are exactly one. And so that can go a long way towards remembering what all happens here. Okay? It saves you a lot of memorization. The more complicated case is the concave mirror and converging lens. And the reason why is because for a converging lens, there is a complete huge difference between whether the object is outside the focus or inside. If you're outside the focus, the lens is able to do what it's named for, converge things. So what you will get is that the image will be DI is positive, it will be a negative magnification, it will be a real image that you can capture on a film or a screen, and it'll be inverted. But then you can break its ability to converge things if you bring the object too close. And that's when you bring it inside the focus. When you bring the object inside the focus, you're back to over here. You are going to make a virtual image instead. I think in your lab you got to look back through the lens and see it, although you couldn't capture it on the screen. So definitely have the nuts and bolts of those, just be able to run your stuff through these equations. So there's your classic relationship between objects in image distance and focal length, and then the magnification is the ratio of how tall is the image compared to the object. Note that it is multiplicative, so it makes it twice as big or 3 times as big. The reason I mention this is because a lot of people ask, what about it when you have a 2-lens system? You don't add them, you multiply them. If the first lens makes it 3 times as big and then the second one makes it twice as big as that, you've got 6 times bigger than before, right? Magnification is how many times bigger it is. So if you have multiple lenses, each of them multiplies onto the previous one. And again, you can also find that from the image and object distances. Okay? Again, things that, definitely know the nuts and bolts for single mirrors and lenses, and then I can ask you a multiple lens or mirror question. All you have to remember for that is that whatever image is made by the first one, that becomes now the object for the next one, right? And then know definitely a little bit about when I talked about how a camera works, how an eye works, how a nearsightedness and farsightedness things, okay? Obviously couldn't put it hugely on the homework because those are calculational, but those are great places to ask concept questions. So that pretty much covers mirrors and lenses. We're pretty much at the current stage right now. I have all of a minute to try to summarize that, but obviously I'm prioritizing things that we haven't seen in a while. So for the 2-slit, remember that the 2-slit pattern, these successive series of brights and darks, they are measured from the center of the screen, y equals 0 and theta equals 0. The slit separation is d, distance from the slits to the screen is L. And you have your equations for the brights and darks. So they're on the equation sheet, so I don't need to tell you them. The one thing that isn't on the equation sheet that you might find helpful for both the homework and for exams is the difference in between 2 adjacent values. So I call this the spread of the pattern, right? It's between any 2 adjacent like spots. So a bright and a bright, or a dark and a dark. So that's a useful quantity. There are 2 approximations that we make here because we're only interested in a visible part of the pattern. The first one allows us to very quickly get the path difference. So delta L is approximately d sine theta, and the second one allows us to convert theta into y, which is our end goal, is to say where are these features of the pattern. And then we got to the single slit, which is more or less the same thing. The only trick to remember for that is that the pattern does not go on and on and on. It fades out. And the central thing here is twice as wide. So this is 2 lambda L over W. That's the big show in town. It's the brightest. It's twice as wide. The satellite peaks are half as wide. Okay? So I think that the homework questions on this stuff are really indicative of the level I expect you to know this stuff. That also goes for the thin film stuff. I gave you a really idea of what that problem solving strategy will be. So if you can solve the thin film problems on the homework, you're good to go. So basically figure out if you got a hard, a soft, whatever, hard, soft. Pick whichever equation is appropriate for what you're trying to find and solve for either the wavelength if you're given the thickness or the thickness if you're given the wavelength. That takes us into photons, which you can deliver power either by changing the frequency of photons or the rate. And then, of course, using the idea that the energy of one photon is hf took us very far in the photoelectric effect, and then the Bohr model, which we actually tied into the photoelectric effect today. Okay, so that's all I'm going to have time for. If on Tuesday we can do whatever you want, so whatever last minute questions you have in the morning, I'm happy to take.